Matrices are used for encoding and decoding messages. To start using this method, you have to change your letters into numbers. Here's what I'm going to do in this case. You just number the alphabet, and you probably want a space so you can put words, and you might also need to even out. You've got to break these into, well, you'll see how we have to break them. Depends on the size of your encoding matrix. So you'll need a space. You might need a spacer in there, so I'll let that be 27. Or you might be familiar with a little better way of numbering letters, and that's the ASCII code. Here's a listing of the ASCII code. You see a lot of the punctuation also has, here's number 61, it's an equal sign. Numbers are also numbered, but not with 1, 2, 3, 4, 5. And then you have different numbers depending on whether it's capital letter or lowercase letter. And of course the ASCII code includes certain commands for the computer, which may be useful in your message. There's an extension to the ASCII code that includes some other letters from like the umlaut and other letters that you might need in sending your messages. Here's your Greek letters over here, and there are other codes that are also used in computers. But what I'm going to do for this is just take that alphabet and number it, and also give number 27 for the space. Somehow you have to turn your message into a number in a consistent way. So once you have a way to number your letters or whatever you're going to have in this message, then you take your message, I'll just say hello, and you write it in numbers. So this would be 8, 5, 12, 12, 15. Because H is the eighth letter of the alphabet, E is the 5th letter of the alphabet, etc. And now you take this message and you run it through your encoding matrix. This is a matrix that codes your matrix. That numbering the letters is not much of a code. So here I'm going to use this for an encoding matrix. It's just going to be a 2 by 2 so that we can get a decoding matrix out of it fairly easily. So you get a new message. I'll call M the message. And you have to make a matrix out of your message. So here's my message here, and I put the numbers together in some sort of way. You could do it where you go 8. For example, you could have, what is this? You could have gone like this, 8, 5, it wouldn't have mattered, 12, as long as you're consistent. And the person on the other end also knows what you did. Okay, so I went 8, 5, 12, 12, 17, but I need to be able to multiply by this encoding matrix. Remember, when you multiply the number of columns, number of columns in the first matrix has to equal the number of rows in the second one. So what I start off with is some kind of square matrix, it has to be square. So if I start off with a 2 by 2 matrix, then I have to construct a message matrix that has 2 rows so that I can do matrix multiplication. And then it's however long your message happens to be, and if it doesn't come out even, you can put the 27 for the space. So I'm going to take this encoding matrix and multiply my message. So here's my encoding matrix, here's my message, and I multiply these together. So if you can recall matrix multiplication, you take the 5 and the 9, so there are one block of numbers, and you turn them and go against the first column, which is 8 and 5, except I've obscured that terribly. Okay, so let's try it again. So you take the 5 and the 9 and you go against this 8 and 5. So 5 times 8 plus 9 times 5 gives me my 85. And you just continue. Now take the 5 and 9 and go against the 12 and 12, and they'll go against the 15 and 27. Then you pick up the second row and you do the same thing. The 6 and 11 multiply the 8 and 5. And then the 12 and 12. And then the 15 and 27. And here is my coded matrix. It's not very sophisticated, but that's how it is. So this is a matrix I would send. Here's my message I would send. It would be 85, 103, 168, 204, 318, and 387. You see matrix multiplication, it's that combination of addition and multiplication, and so it just merges these numbers together and multiplies them all through. And this is the matrix, and this is my encoded matrix, which I'm calling C because it's coded. The person who gets the matrix has to decode it, and this is where some matrix rules come in. I want to take some matrix, I'm going to call it B, and multiply my coded matrix and get back the original one. Right? But what is the coded matrix? It's the encoding matrix times my original matrix, and I want that to be my original matrix. Remember, I just substituted for the coding matrix, because to get the coding matrix I multiplied by the encoding matrix A and multiplied my message by that, by A, the encoding matrix. Okay, if you look at that equation, what does that mean? That means B times A has to equal I. The only way that's true is if B and A are inverses of each other. That's a test, a question on the test. You find two matrices, when multiplied together, they equal the identity matrix, then the two matrices must be inverses of each other. So B has to be the inverse of A. This is why we used a 2 by 2, and that's what this is all about. If you took the inverse of A and you multiplied MC, that would be like multiplying the inverse of A times M. But A inverse A is the identity, and the identity times M just gives you M back. So this is what you've received, and that's what's here. So now you have to find the inverse, and either you had the original matrix or you construct the inverse matrix. We're going to have to construct it in this case. So here was our encoding matrix, and it's a 2 by 2. So first you have to determine if it has an inverse. If it has an inverse, its determinant is not 0. So I take the determinant of A, and that will be 5 times 11, which is 55, minus 6 times 9. Remember, multiply this way, then multiply that way. Minus 54, that answers 1. It's not 0, so that inverse exists. And let me write you here the formula for the inverse of a matrix. I'll clear this off a little bit. Okay, so here, if this is a generic 2 by 2, A, B, C, D, its inverse is 1 over the determinant, which is AD minus BC, and then in this matrix the diagonal terms switch, so you have a D and an A, and the off-diagonal terms become negative. So that's that would be the inverse matrix. So what we have already is that AD is 55 and BC is 54, so that's here, taken care of. Now the 5 and the 11 switch, you can see that right here, and then the 9 and the 6 change sign, and that's my inverse matrix. And now we can see how it works, or if it works. So the coded matrix that the other person received was 85, 103, 168, 204, 318, and 387. Here is the decoding matrix. Remember that we had a leading term that was 1 over the determinant, but the determinant was 1. It was 1 over 55 minus 54, so it's just 1, so fine. We're just left with the matrix. We don't have to worry about a scalar. And now again we have a 2 by 2, so we have to arrange the matrix, or the coded message, into rows of 2. So there's 2 rows in the matrix. And then we just multiply. And when you get done multiplying, look what you have. 8, 5, 12, 12, 15, and then 27 was a space. And that was the original matrix of hello. If you do a Google search under cryptography and look into the Wikipedia article, they have a discussion, essentially the same discussion, but they use a 3 by 3 matrix. But finding the inverse of a 3 by 3 matrix is not as easy as for a 2 by 2, so that's why I just did a 2 by 2 matrix.